All right, so we're back, and I'd like to continue. The last thing we talked about was the lower sum, little s sub n, and now we're going to find uppercase s sub n, the upper sum. I'm sorry. So this m that we're going to be using, which is an x value that produces the largest value of y for that rectangle, is going to be the starting value, a, which in this case was 0, plus I times 2 over n. And that produces the right-hand rectangles. I forgot to start with that. If you recall, the upper rectangles, because it's an increasing function, are on the right side each time. So these create rectangles that extend beyond the curve and beyond the area we're trying to find. And these, of course, are, as I already said, right-hand rectangles. And this is the formula that you'll use for this problem to get the x value of each right-hand rectangle. In general, in fact, this is something you probably want to go ahead and get in your head. What we have just found is that the right-hand rectangle is not necessarily going to always produce the largest value, but the right-hand rectangle will always be the x value, I should say, for that right-hand rectangle will always be the starting value a plus I times delta x. The formula for the left-hand rectangle is more complicated, and as we're going to find out soon, it doesn't really matter if you use left-hand rectangles or right-hand rectangles or other rectangles that actually could be produced. You could always have one that's exactly a fourth of the way between the left and right-hand side, which is kind of silly, or a midpoint one, which is actually talked about quite a bit later in this book. The midpoint between the left and right, that x producing a y value. And if the function, say the rectangle looks like this, and the function is kind of looking like that, then the idea is that if you pick the middle, that y value right there that's created is going to be partly too big and partly too small. And so the hope that there is that maybe it'll be closer to correct. Well, as it turns out, no matter which x value you pick on the subinterval, from the left side to the right side of the rectangle, it will not matter because we're going to be taking a limit, and that limit is going to make them all pretty much be in the same place, and it wouldn't matter which one algebraically you started with. This right-hand rectangle is the easiest to do. The algebra is the easiest it can be, and so I want you to, again, focus on memorizing this. And that delta x, as we already mentioned, is obtained using the formula that I already gave you, b minus a over n. And those are two very important formulas going forward from this. And we'll be able to use those more as we go. So the s sub n, the upper sum, is going to be the sum of all of the rectangular areas from the first rectangle to the nth one of the y value that is the largest possible y value, f of m, capital M sub I, times the width, delta x. And for each rectangle, we'll multiply the height, which is the function output, times the width, delta x, and add up all of those rectangular areas. So in this particular problem, that ends up being Since our function is the squaring function, we'll take our capital M sub I, which is up to the left, that 2i over n, and that's our input, that's our x. So we're going to square that, and so there's our function for the x value, capital M sub I, multiplied by delta x. So doing some algebraic simplification, that's 4i squared over n squared. Oh, and I didn't calculate delta x already, so let me go back and do that. For this problem, our delta x, again, is b, which is 2, minus a, which is 0, over n. So 2 over n. So this delta x will be replaced by 2 over n, which I probably could have done in the last step, probably should have. I have a cat in here. It's distracting me. It's trying to rub it all over everything. It's about to knock a bunch of papers over, so excuse me if I'm just a little bit distracted. I'll try to improve. All right, so this is sigma from I equals 1 to n, 8i squared divided by n cubed. The 8 and the n cubed are both considered constant for this problem, so I'm going to pull them out because the variable of this problem is the index I, so the I is a formula thing, so that I squared has to stay in there, as you can see. All right, so this is going to be 8 over n cubed times n plus 1 times 2n plus 1 all over 6. Do you see how algebraically this one is turning out so much more nicely than the other one did? Okay, the 8 and 6 cancel to leave 4 in the numerator, n cubed in the denominator, and what we're left with otherwise is n times n plus 1 is n squared plus n. Multiplied by 2n plus 1. So that's 4 over n cubed times 2n cubed plus 3n squared plus n. And then when I distribute the 4 over n cubed, that's 8. Oh, bother. I'm sorry, I dropped a 3. It's 8 divided by 6 is 4/3. Let me go back and put that 3 back in where it should have been. My apologies. And of course, this is not 8, it's 8/3. There we go. Plus, then that'll be 4 over n plus that'll be 4 over 3n squared, which is the upper sum. So the next task would be, for this particular fairly easy problem, would be to, whoa, sorry, I hit the wrong thing. Let me get back to where we were. Sorry about that, I messed this up pretty badly. Let's see if I can get us back to where we were. We're close. I'm sorry about that. Okay, so as I was saying, what I want to do now is find the limits as n approaches infinity, as the number of rectangles goes to infinity, of both of the upper and lower sums. So the limit as n approaches infinity, that's not a very pretty infinity, my apologies, of the lower limit s sub n will be the limit as n approaches infinity of the formula we found in the last section, which that was 8/3 minus 4 over n plus 4 over 3n squared and as n goes to infinity, the limit of the constant 8/3 is 8/3 minus the limit of a constant over n as n goes to infinity heads towards 0 plus 4 divided by 3 times an infinitely bigger thing. That fraction 4 over infinity is headed toward 0, and so that's headed towards 8/3. So that's the lower limit, or the lower sums limit as n goes to infinity. If we do the same thing for the upper sum that we just found, you'll notice very quickly that the limit for it is going to be exactly the same number we just got for the lower sum. It's also 8/3. So as you can see, our actual area, therefore, is 8/3 because the two limits approach the same value. And if that's the case, then the thing that's between them has to head toward 8/3 as well. So that's a really nice result. And algebraically, I will say that the right-hand sum is the easiest one to do algebraically. So if you look at the next page, there's a theorem here that says that the limit of s sub n, the lower sum, lowercase s sub n, and the uppercase s sub n, those two limits will always be equal if f is a continuous and non-negative function on the interval from a to b. So it does not matter which one you do. And so because the right-hand sum is the easier one algebraically, that is going to be our preferred one. So I'm hoping that we aren't going to be finding both and finding out that they're actually equal, because it seems like a silly thing to do that. Now, something that we use that I didn't really talk that much about yet is we use something called the squeeze theorem. Let me move my screen down so that I can draw this. But basically what it says is that if you have two functions, two items, and that's what the exhaustive method is actually based on, is this. If you have some function like g of x, and you have some other function, let's say it's h of x. And let's claim that we know that at least from a to b, so on the interval a to b, for sure. So I guess I better write in where a and b are. On this interval from a to b, we know that this is always true. H of x is always less than or equal to g of x. If we know that that's always true, from A to B. That's our starting point. Now, let's assume those two are things that are easy to do and easy to find what those limits are as x approaches some value. Put that on here. Some value c. And so that finding the limit as x approaches c for g of x and h of x is easy and doable, and the answers are the same. For the g function and the h function, the limit as x approaches c for the g function equals the limit as x approaches c for the h function. And now, let's say that there's something we don't know much about, don't know how to do it, but we can claim for sure that at least between a and b, this other function is always between them, at least from a to b. So we're going to go in and now say that there's some function f that we don't know a lot about, don't know how to deal with it very well by itself, but because of the two functions we do know about, the g function and the h function, if the inequality is now writable as h of x is always less than or equal to f of x, which in turn is always less than or equal to g of x. Because of the limits for g and h as x approaches c, we can claim that if f is truly between f is truly between h and g, always, then what we can claim about that is that we know therefore the limit as x approaches c for the function f of x will also have to be exactly the same. So let's go back up here and call this L, so I have a name for it. The limit that they share in common as x approaches c for both g and h, let's call that answer L. We can therefore claim that the limit for f would also be L as x approaches c. And that's basically what we were saying, was the upper sum and the lower sum are bounds between which our answer has to lie. And so if those two, one's too big and one's too small, if those approach the same value as n approaches infinity, then our actual area answer has to approach that same value. And as it turns out, lost my train of thought. I'm sorry, the cat's bothering me. I'm sorry, I thought it'll probably come back to me at some point. Just not clear right now what that was going to be. Sorry about that. But so our actual area can be calculated using either the left hand, right hand, or midpoint even, or whatever one you want to use. They're all valid, and so algebraically we are going to pick the one that we perceive to be easiest to deal with, which is the right-hand rectangle. That's going to be our call on this. Because we can make it that, we will. Because I just promise, just believe me, that is going to be the best that we can do. All right. So this, by the way, that was called the squeeze theorem that we were just talking about. It's the name of that. Some also call it the sandwich theorem. So what we're going to do is we're going to say that we can find the area of any region of the area of a region in the plane for any non-negative function f, and it needs to be a continuous function, by the way. We can do that using this formula: the limit as n approaches infinity from the first rectangle to the nth one, if we take f of some value of x, we're going to call that x value, that generic x value, c sub I for right now, times delta x. So that f of c sub I gives us the height of the rectangle, delta x gives us the width, and that's going to provide us with the exact area. And it doesn't matter actually if that's a left hand, right hand, whatever value c is that's producing the height of the rectangle, it doesn't matter where it is. And as I said, we're going to use the one where it's the easiest. We're going to therefore, as I said earlier, use for delta x, we're going to you have that formula b minus a over n, and x sub I, which is what I called it earlier, which in this formula I guess we could call it c sub I. That's what I called it earlier, is x sub I, is always going to be a plus I times delta x. And that will always give us the exact area. All right, I'm going to pause this, move the cat out of the room so that I'm not as distracted, and come back later.